Welcome, everyone. It's my great pleasure to host Marc Deisenroth here for our seminar today. A lot of you might not know this, but Marc had a profound influence on my life because he's the person who introduced me to my PhD advisor. So, for him, I might not be here today to host Marc. So, very well in advance. Marc would still be here though, because he actually has a very impressive resume. So he's currently a professor at UCL, where he is leading the sustainability and machine learning group, focusing on data-driven learning and autonomous decision making. He's also a visiting faculty position at the University of Johannesburg. He is the UCL DeepMind Chair of Machine Learning, the Deputy Director of UCL Center for AI, and part of the UCL UNESCO Chair on Artificial Intelligence. Previously, he's also been a visiting lecturer at Cambridge. He's been an imperial lecturer. He has been a group leader at Taylor Johnstown, and he did his master's and PhD in Karlsruhe Institute of Technology. And one thing I do have to point out is the end of it is the bio, which I think I loved it. So applications in weather, nuclear fusion, and robotics. If that doesn't sound like a mad scientist, I don't know what does. But with that, I'm going to hand over to
Thanks, Oliver, for the introduction. But if you weren't here, I wouldn't be here today either, because I wanted to visit you. So that was the main point why I'm here. I can be honest here. So thanks everyone for coming. I'm aware it's an unusual time. It's also quite early in the day for some people. So I appreciate you coming. I hope I don't disappoint you too much today. I want to talk about data efficient learning for robotics and reinforcement learning. And okay, that obviously doesn't work, which is good. Yeah, so I just wanted to start maybe with some machine learning success stories, which you may have seen before already. So machine learning has made great progress recently or in the last decade in things such as gameplay, whether this is Go or other computer games, text, image, speech generation, or protein folding. I think really remarkable success stories of machine learning methods. The important ingredient, or one of the important ingredients to all of those success stories, is lots of data. And that's something I don't want to focus on today. I want to focus on settings where we have small data situations, for example, when we have rare events, if we look at data that comes from the Large Hadron Collider, or where data collection is expensive or time-consuming. So we're looking here, for example, at robotics, where you can't conduct experiments, real-world experiments, faster than real time. It would be great, but that doesn't quite work. Or where data is scarce. So if you work in low-resource languages, then you don't have enough data. So you need to think about how to use available data more efficiently. So a key point here is, if we look at these kind of situations where we don't have much data, we need to extract more or better information from the data that is available to us. And that is what I kind of like coin data efficient learning. And a couple of aspects to data efficient learning that one could consider, and this is not an exhaustive list, just a few things to maybe mention in the context maybe of this talk about maybe data efficient learning in robotics. We can think about model-based reinforcement learning, where we build an emulator of an environment and use it for planning. So once we have a good emulator or simulator, we don't need real-world experiments, theoretically. Imitation learning is another way to use data efficiently, where we use demonstrations as a seed for learning. So there's a good prior or bias for learning. Transfer learning as a way to generalize knowledge to related tasks. So if we have already like solved a bunch of tasks and there's a new task coming in, can we transfer knowledge from the old task to a new task? The hope is also, again, to speed up learning there. We can use some structural priors, for example, by incorporating constraints from physics or mechanics. Or we can do offline RL, where we use offline data, which could come from other tasks, again, for learning. So all of these are, 5 different ways to kind of like think about data efficient learning in the context of robotics. Today, I want to talk about 3 ways of doing data efficient learning in robotics. So one is model-based RL for data efficient decision making. One is transfer learning, where we use latent variables to generalize knowledge to new tasks, and offline imitation learning, where we combine expert demonstrations and large unlabeled data sets to learn good policies. And before I go into like these individual parts of my talk, I want to give a quick shout out to my collaborators. In particular, I want to highlight Steindor and Ichang, who have done a lot of work, or most of the work, in some of these topics that I mentioned. But also Samuel and Zheng Yao, Ed, Katja, Carl, and Dieter have contributed greatly to these projects. With that, I want to maybe kick off with model-based reinforcement learning. And I want to set the scene just very briefly. We're looking at a setting where we have a state, which I denote by x. The state at time step t plus 1 is a function of the state at time step t, and a control signal, which I denote by u. The control itself is a function of the state and a bunch of parameters. This function is called policy. If you do control theory, it's effectively implementing a state feedback controller. The objective now is to find policy parameters, theta star, that minimize an expected long-term cost. And the expected long-term cost I'm going to denote by j of theta, which is the sum of finite horizon costs or expected costs at every time step. This cost could be a squared distance between, let's say, me and the coffee machine, right? I want to minimize that distance over time, get to the coffee machine as quickly as possible. That's an example of an instantaneous cost. So this kind of objective is typical in RL, but also in optimal control. Roughly speaking, I would say the difference between RL and optimal control, at least in this kind of formulation, is that optimal control assumes that this transition function f is known, whereas in reinforcement learning, you don't know that function. And I want to consider the reinforcement learning setting today. So I'm going to walk you through like 4 high-level steps of an algorithm for very fast learning, reinforcement learning. And so what this algorithm does in its first step is it learns a model for this transition function that we don't know. So we're going to use a probabilistic model for this function, and you can think of this as a way of doing system identification. So once we have this probabilistic model, we can use this model to compute long-term predictions of the state evolution given a particular controller parameterization. Once we have that, we can improve the policy. And once we've done that, we can take the policy and apply it to the real robot. So in these 4 steps, the only step that requires an interaction with the robotic system is step number 4. And once we have applied the controller, that means also we get more data, real-world data, which we can then feed back into the probabilistic model, and we're going to run through all of these steps again. So we just cycle through these 4 steps. And I want to maybe shed some light on the inner workings of all of these 4 steps, maybe in the next 5 to 10 minutes. So let's maybe start with the probabilistic model learning. Effectively, what we need to do is we need to solve a regression problem. Now, assume we have inputs x and outputs y, and we have a bunch of observations. In this case, we have 8 observations. So model learning now means finding a function that connects all of these observations. Illustration purpose, all of this is noise-free. So the function goes through these data points exactly. So we can solve this regression problem in various ways, but here's a solution to this. Yeah, so we fit a function, it doesn't have any training error, and now we could use this function for reinforcement learning, right? So this is now a 1-step predictor. So now we use this function to make a prediction, and based on the prediction, we can make a decision. So now let's do this. We're going to predict at x equals 7, our function value is around -1, and -1 will incur an action that says accelerate. who would be happy with that decision here? Or who would be happy, let's say start, who would be happy with this prediction? Who is unhappy with that prediction? Okay, why? Suggestions. Good, yeah. So this is a prediction that we make at a point that is very far from the training data that we have. And you rightly said extrapolation is a potential issue here. We may be more confident predicting at maybe 2.5, 2.5 or so, then we're kind of like ballpark okay with the red line, probably. So yeah, so the issue now is we could also fit different functions. They would make different predictions, and these predictions would lead to different decisions. So now we have this issue that these kind of like, I mean, neither of these functions is the correct answer with very high probability. And that means particularly in an RL setting where we have to do this multiple times or iteratively, we have compounding model errors. And effectively, that means it's very difficult to find a good policy. So what are we going to do about it? So we suggest to express kind of like what we know about the model and what we don't know about the model by placing a probability distribution over the class of functions that we consider. So now we have something, well, the model itself is represented in this kind of like way where the black line is the average function that we believe, models the data. And the uncertainty is represented by this shaded area. So the bigger the area, the more uncertain we are. Now, if you make a prediction at x equals 7, then this model would say, well, on average, I think it's 0, but actually, I don't really know what's going on. And that's maybe a fairer assessment to the previous prediction, which says, well, it's going to be this value or that value. Now, if we take this uncertainty into account when we make decisions, we're much more robust to modeling errors. And that's kind of like what we want to do. So key point here is we need to express uncertainty about the underlying function to be robust to model errors. And we implement this distribution over functions using a Gaussian process. If you don't know what a Gaussian process is, that's perfectly fine. It looks like this, and that's as much as you need to know for today. It's a distribution over functions. The equations don't really matter.
So then you have Gaussian processing, or you need sort of uniform error bound from Gaussian process.
So the posterior uncertainty is enough. That's the only thing that we're gonna consider today. Yeah. Good. So now we know how to learn a model. We use this Gaussian process, and now we want to predict the state evolution given a controller parameterization. What that means is starting off with an initial state distribution at time equals 0, we're going to push this distribution through the Gaussian process iteratively and compute the state evolution at time step t equals 1 up to capital T, so for the finite time horizon. Now, I'm going to pick, it's just one time slice out to illustrate what computational challenges we face. Now, let's assume at this particular time point, we have a Gaussian input distribution on the state and control pair. We want to map it through the Gaussian process. So I'm kind of like color coding the corresponding distributions and in the equation here. And if we do this, we get this red distribution up here. So it's multimodal, but in order to compute this red distribution, so the distribution of the state at time step t plus 1, we have to solve this triple integral where we integrate out everything that's uncertain. So we integrate out state, control, and the function itself, because we do have a distribution on the function. So unfortunately, we can't do this in closed form. So we can't compute this red distribution in closed form. But what we can do is we can compute the mean and the variance of this red distribution analytically, and then we approximate the red distribution with a Gaussian that has the correct mean and has the correct variance. And then we're going to take this Gaussian, kind of like push it back at the next time step and cycle through these kind of like approximations to get these state predictions or the state evolution that we are interested in. Keep in mind, this is all approximate, but it's in closed form. So now, in order to improve the policy, we'll do the following. First, we compute the expected long-term cost, and then we find parameters that minimize this cost. Now, let's have a look at how to compute this long-term cost. We already have Gaussian approximations of the state at time step at all of these time steps. And in order to compute the expected long-term costs, we have to compute an expected value of the costs at every time step. So in order to do this now, we have to solve this integral. And because these state distributions are Gaussian, and we can often solve this or compute this expected value in closed form. So if we choose the cost function to be a polynomial or many trigonometric functions, Gaussian-shaped functions, we can solve these integrals in closed form as well. That means now, putting everything together, we can write down maybe a lengthy equation, but we can write down an equation to compute an estimate of this expected long-term cost analytically. There's no sampling or anything involved. And that also means you can compute gradients analytically, or you can use automatic differentiation, and then use a gradient-based optimizer such as BFGS to find good controller parameters. Okay, and then we are at the point where we have to apply this controller to the real system. And for this, I thought I'll show you a small demo. Oliver knows this one, I guess, still. So we were looking at this cart pole swing up problem where we have a cart that is running on a track. There is a freely swinging pendulum attached to it. Initially, it's hanging down. And the idea is, or the objective is, to find a control strategy that pushes the cart to the left and to the right, swings the pendulum up, and balances it in the inverted position, where the red cross is. So the state of the system is the position velocity of the cart and the angle and angular velocity of the pendulum. We don't make any assumptions about the nonlinear dynamics because we wanted to show that it is possible to learn from scratch by just making, the only assumption we make is that we have relatively smooth dynamics. As a cost function, we choose this particular one here. Let me briefly explain what that is. So this squared norm here is the squared Euclidean distance between the tip of the pendulum and the red cross. No velocity penalties, no control penalties. It's really just Euclidean distance between the tip of the pendulum and the red cross. And then we're going to do 1 minus an exponential of the negative squared. What squared cost? What this looks like, it looks like kind of like a valley, which is like 1 minus a Gaussian shaped function. So if you're completely missing the target, it saturates at 1. And if you're close to the target, it's locally quadratic. But it doesn't go to infinity, which you would have with a squared cost. It saturates at 1. Okay, so now let me, okay, obviously not. But let me show you how this works. So we start by collecting, applying random actions to the system and to collect some initial data to learn the Gaussian process. We do this twice. So each of these trials is 2.5 seconds long. It's a 10 Hertz control frequency. So we have 50 data points after these 2 trials, or 5 seconds of data. So now we take these 5 seconds. We train the Gaussian process. We do long-term predictions, optimize the controller. And then we come back to the system, to the cart pole system and see what happens and try the controller out. So that is what happens. So it kept the cart in the middle of the track, but it didn't really get the swing up movement. If you look at the predictive uncertainty, it explodes after 2 or 3 time steps because it never had any data in this regime where, or part of the state space, that it just exploded. Because the random data was just more or less uninformative. But now it has data in this area, and it now knows, so after updating the Gaussian process, that wasn't an ideal thing. So it now optimizes or re-optimizes the policy, and it tries something different. So what happens now is that it gets this kind of like swing up movement, and it's very excited about getting the idea of the swing up movement. So it's overshooting. But again, it's collecting data in the part of the state space that it hasn't seen. And now it takes that into account when it updates the policy. You can see here in every single trial a significant improvement of the policy compared to previously. This is usually not what you see in reinforcement learning algorithms. So now we are in, I think, trial 6, 12.5 seconds of data. It almost got it, and it will now solve the problem in the 7th trial. So it gets the pendulum up and inverts it in the, balances in inverted position. Laser pointer is approximately where the red cross is. Remember, it only penalizes the distance to the laser pointer. And it's even robust to small disturbances because it's a feedback controller. So that's kind of like how this works. Yeah.
So like how much is performance dependent on the choice of kernel functions?
So that's a
RBF or in the design some kernel functions.
So it's a good question. So we use an RBF kernel, but also for computational reasons, because you can't do the moment matching, so the kind of like Gaussian approximations with the Matern kernel, for example. But the RBF kernel is fine here because the dynamics are smooth.
And yes, what if the dynamics not in RHS? Like what if the dynamics is not be reported?
So then things become complicated. So if you have dynamics with contacts, for example, don't do this. Bad idea. I can tell you a little bit more about this. I mean, we tried and failed. And then we did something else to solve that.
GP is
yeah. So the highest dimensional system we did was, I think, 27 dimensions. But the dynamics were simple. And then we also got away with relatively little data. This is more like for illustration purposes. Yeah. Yeah.
Do you have to explicitly handle the topology of data?
No. So really, this system was, I don't know, dumb in a way. It's like, okay, let's just try. If you build in topology in a way, I believe this will learn faster.
You have the more complicated the Gaussian process is, but because it becomes bigger, the more.
Yeah. So the more
scale to.
So the more data you have, the more computationally involved this becomes. And at some point, you can go to work with sparse Gaussian processes, and that's also fine. But so one thing that you maybe you think, okay, training scales cubically in this regular Gaussian process. Training is not the problem. The long-term predictions are the problem, because you roll, let's say you roll out over 50 time steps or something like this. So you have to do this approximate inference 50 times. Then you get one function evaluation. So now you run a gradient descent on this. So you do this about maybe 200-300 times, these 50 evaluations. So that gets you to 1,000, 1,500. And that is the thing that really slows it down. The training is fine, but the inference takes a while, or the optimization takes a while.
Or a separate Gaussian process for each dimension of the output space.
Yes. Yeah. Most simple setting. So you can correlate the outputs. That's fine. This is really the most simple setting where we have independent Gaussian processes for each output dimension.
Neural networks can give you approximation of the posterior after.
Yeah, but here you get the posterior for, I don't want to say for free, but it's a bit of compute, but you get the right answer. And I don't necessarily think that a neural network is a good model for regression. Because again, like for a Gaussian process, even if you don't do anything, you have an automatic regularizer in there that gives you, I think for regression, a Gaussian process is a good solution if you work in low, medium dimensions, and you don't, well, even the number of data points is a solved problem by now. Okay. So in terms of, yeah, so I started off with like data efficiency. How much data do we need in order to solve these problems? This work it's been a while since we did this. It's more than 10 years now. So these references are not completely up to date, but at the time, these ones are algorithms or methods that looked at the same kind of like problem. Okay, all of this is in simulation, but it doesn't really matter. You have most of these methods are model free. I think the first 4 of them are model free, and they require either days or hours of data collection. This one is a model-based method that used neural networks, but compared to the state of the art at the time, we could report an order of magnitude faster learning and report an unprecedented speed up or learning speed compared to the state of the art at the time. So that was encouraging because we didn't really, as I said, we didn't do a lot, right? We used a standard Gaussian process with a standard kernel. It's really just the way of thinking about how to propagate uncertainty over time. And that was pretty much the key point here. And because of these relatively general assumptions, we could also apply this kind of idea to a bunch of different problems. So here we used an off-the-shelf cheap robot arm, as I think $300 at the time, to learn to stack blocks. This one was work in Darmstadt, where we used a tendon-driven robot arm to learn to hit table tennis balls. This one was also back in Darmstadt, where we used this KUKA arm to learn curling. And then other people also use these methods to do hierarchical reinforcement learning, to learn pitch control of a unicycle, or to control throttle valves in combustion engines. It's the same algorithm, same kind of code. You can do a lot of things. So the point here was that I wanted to motivate that data efficiency is critical in robotics, for example. And we talked about a probabilistic model-based reinforcement learning approach that reduces the effect of model bias, that achieves an unprecedented learning speed, and it's widely applicable to robotic systems with caveats, in terms of dimensionality and don't have contacts. I think then this works. Yeah, please.
But nowadays we got Isaac Gene, we got Majorca 3Ds, like GPU parallelable simulators. Why does data efficiency for AI or robotics even matter now?
I mean, I think as soon as you go and work with real robots, right? So either you solve the sim to real problem. So Majorca also doesn't have perfect implementation of all kinds of friction or contact, right? They're always like idealizing or idealized assumptions. So in that case, if you work with a simulator, it doesn't matter. But if you work with a real robotic system, and you need to collect data from the robotic system, you have to think about what you want to do with that data and how you use that data efficiently.
You said that the system struggles with setups where there's context, but then you showed that it works in like manipulation environments or setup where like they hit a ball where there's like very clearly context.
Oh, okay. The table tennis hitting ball doesn't change the dynamics because the table tennis has like, well, it's like 2 grams or whatever, right? Doesn't matter. That's fine. And the block stacking was not, we didn't do the manipulation problem, just put the blocks in the gripper. So there's no grasping involved. So it was a very simplified setting. But yeah, fair question. Okay, so in the second part, I want to talk a little bit about transfer learning. So here, think about if you were to learn predictive models and maybe controllers of different hardware systems, imagine maybe these robot arms, they, are all different, but they're all the same in some way, right? They have the same number of links. They may be different lengths. Maybe the motors are a bit different, but in some way, there should be an opportunity to transfer knowledge from these two robots to the other two robots because the problem setting looks very similar. Yeah, so we can make a smoothness assumption that the overall dynamics should not be too dissimilar. That means these dynamics or these robots share some global properties, but locally they may have different configurations, for example, masses or link lengths. The idea that we wanted to have is to reuse experience that we have collected so far to generalize learning, to generalize, well, the knowledge that we have in order to learn new dynamics that are similar to the ones that we have already seen, and that use the collected data from other robotic systems or other tasks to, in some way, warm start learning a new task. And what the approach we are following here is a hierarchical Bayesian approach. And I want to briefly introduce you what the model looks like. So if you look at a standard supervised learning task where you have something like y of t is a function of, so y are the observations, is a function of some inputs and a bunch of parameters. So a corresponding graphical model could look like this, where so yeah, yt is a noisy observation, theta are unobserved parameters, and x is a deterministic input. If we go to a multitask supervised learning where we assume independence between tasks, and we take this entire setting that we had and give every task, so tasks are now p, as we have p tasks, every task has a different set of parameters. So there's no like information sharing between tasks. So that would be the corresponding representation here. And if we look at, so we are considering a meta-learning setting where it's a bit of a mix between the two settings that we had, but we're going to introduce an additional variable, which we're calling h. So this meta-learning setting, so we can now write that the observations are a function that is globally parameterized by theta, so as previously with some inputs x and task-specific parameters h. So these, this latent variable HP describes a local configuration, so that could correspond to a link length or a mass of this robot arm. So this is really task-specific information, but these theta parameters, they capture global properties of the model, and they allow us to share properties between tasks. So I'm going to give you an example of what that looks like. So we've already seen Gaussian processes in a way. So we're going to look at tasks where we have observations of functions which are offset from 0. The functions are identical, they're just shifted. So training data, so here we have two tasks. Training data is these black dots. So we have maybe half the function covered in one task, half the function covered in the other task. And so this should be something else. But if we now run this model that I introduced, and we again like a Gaussian process where we have this augmented latent variable, this h task-specific latent variable, then we make predictions at these training tasks that are relatively well informed. So although we don't have training data for this particular task in this area, it does make confident predictions and good predictions, although we don't have training data here. And the same for the task below. These predictions are good. And the only thing that we need to infer, so the latent variable encodes the offset from 0 or the bias of this function. That is what the latent variable does. Now, if we were to give one new test data point of a task that we have not observed, what we're going to do is we're going to make an inference about what the offset or the latent variable is going to be. And then we use the shared global parameters, so which encode the shape of the function, to make predictions. And so that is the corresponding prediction by having just one observation that allows us to infer that task variable. And that prediction is confident and informed. So the black function is always the ground truth. So we can do this with interpolation. We can also do extrapolation. So we're going to go to down here where we don't interpolate between two functions that we have seen already in our task, but we can go and extrapolate. And these predictions are they are good, not relatively good, they are good. So you can do one-shot predictions at new tasks using this kind of framework. So what we did, so now with this kind of setting, we're also going to go back to the card-pole system that I introduced earlier. What we wanted to do is we want to learn dynamics and controllers for different card-pole systems where we vary the length and the masses of the pendulum. So this is in simulation, not in hardware. We use a model-based RL algorithm, which is pretty much the same that I introduced, but instead of like learning a policy, we do model predictive control. That's pretty much the only difference. So here's what we did. So we have, I'm going to show you this grid over here. We have masses on the horizontal axis that go from 0.9 kilograms to 0.4 kilograms. And the length of the pendulum varies from 40 centimeters to 70 centimeters. So bottom left, heavy and long. Top right is short and light pendulum. The disks here are the training tasks. So we give training data from these 6 tasks, and the circles are test tasks. Now, we learn these latent configuration, these local parameter, these H parameters, using variational inference, and we embed them in a 2D space. And when we do this, this grid transforms into a slightly skewed grid. What you can see here is that it clusters dynamics more in the bottom left corner. And what that means is that these tasks are relatively similar to each other. So in the context of this setting that means that the dynamics for long and heavy pendulums are relatively similar. That is what this clustering means. Whereas if you have a short and light pendulum, the dynamics are very, very different. So this is kind of an outlier over here. So now, in terms of like comparisons, so what we did, we wanted to few shot generalization on 4 unseen configurations, and we defined. So we trained on six different configurations and evaluated on 10. So that you don't want to unlearn the 6 training tasks, but you want to additionally learn the 4 new test tasks. That is what this means. Success means solving all 10 of those tasks. And we used, so the orange line is where you just use an independent Gaussian process model for every task. So there's no transfer happening. And you can see after maybe 7 trials of this card-pole system, you get to about 90% success rate, which is fine. Then this green line is you just ignore the task-specific latent variable and just pretend all the data sets come from one big system. So that has a good warm start here with a 40% success rate, but it will never make it to the 80 or 90% success rate, because the only way to explain different dynamics is by increasing the noise. That's the only way that this one can explain it. And then if you do this meta-learning approach with the latent variable, it also has the warm start, but then it also very quickly gets to a high success rate. So after five trials, you get to, or 6 trials, you get to these, to a very high success rate. So what this means is it doesn't only not unlearn the tasks that it already learned, but it also generalizes well to tasks that it hasn't seen yet. So to summarize this part, I wanted to formulate meta-learning as a hierarchical Bayesian inference problem. We can automatically infer similarities between tasks via these latent variables because we learn these embeddings. We can speed up multitask reinforcement learning, and we can also do few-shot learning of new tasks by transferring knowledge from old tasks to the new tasks via these global parameters. So now, the very last bit, I want to say, yes.
The motivation for the target that was for the bias for GP.
Oh yeah.
Yeah. So I'm curious, like, what if you learn rather than learning a bias as a later, you learn a weird indicator function. If X goes to the first part, you feed to the first like class or black point. If X goes to the second part, it fits the second part of the black pawns. Yeah, any mechanism to stop it from learning a weird latent variable.
So if I understand correctly, then you would need to have a fixed number of clusters or classes beforehand.
In this particular example, since the two groups of black pawns, they don't overlap, hypothetically, I can learn another latent variable as well, rather than learning fast. That is, if X goes to the first part, I will feed to the function below. If X goes to the second part, it feeds the function above.
So if you were to fit only one, say, if you just were to train a Gaussian process on this data and ignore this data set here, your error bars would be exploding in this area. So already like just having these small error bars is only by getting transfer from here to the other task.
How about the neural network? Oh, sorry, the Gaussian indicator function. If X goes to the first part, you will feed to GP model 1. If X goes to the second part, you feed the GP model 2.
Okay.
That perfectly feeds this black pawn. That is going to overfit into the new orange pawn, right? Because the orange pawn will go to the second part of the data, but it will give you wrong. It will give you model 2. So just wonder any mechanism to solve this. Because here it's like this two like a group of data.
Maybe this would be a good.
Yeah.
Maybe we should take this one offline. This question, I think.
Yeah.
Okay. Yeah. Thanks. We'll discuss this later. Yeah. No, that I think is a great question. We can talk about this later. Just maybe last few minutes, I want to briefly talk about some ideas on offline imitation learning. So the setting that we're considering here is we have a large amount of data, for example, robot trajectories from various tasks or motor babbling or whatever. The data is not generated by an optimal policy. We don't know what policy that data set came from. And the goal is to use available data to find an optimal policy from this static data set without collecting more online data. So it's pure offline learning. The properties we would like, if we can solve this problem, then this is a good approach when online interaction is impractical. For example, data collection is expensive. We want to reduce the amount of, interaction with the robot in the context of data efficiency. The additional assumption that we have in our setting here is that we also have unlabeled data. So all this data set, this offline data set, doesn't have any rewards. It may have actions, but no reward labels. Now, the question is, what are we going to do with this? So we have this unlabeled reinforcement learning data sets and a data set. If we have recorded actions, we could run behavioral cloning. But that is suboptimal for mixed quality data sets. So if we have high quality trajectories and maybe not high quality trajectories, there's some other issues with general like overfitting problems. If we wanted to do offline reinforcement learning in the setting, we would need to have some form of labels because we need some form of reward function. Now the question is, if we don't have those labels, how can offline reinforcement learning leverage a large amount of unlabeled offline experience? And that's kind of like the question that we want to solve or to answer. Now, what we now assume to address this question is that we have one expert trajectory given or expert demonstration given or a few of those, but at least one. Now, I think you can imagine where this is going. We will use now this expert demonstration to add rewards to unlabeled reinforcement learning data sets using this yellow box here, which is optimal transport reward labeling. But this is a mechanism for automatically adding labels to the reinforcement learning data set by incorporating the expert demonstration. I'll tell you a little bit more about how this goes. In that sense, so once we've done this, then the originally reward-free data set can be used by any RL offline or offline RL algorithm. And effectively, what we do is then an offline imitation or have an offline imitation learning framework. So here's kind of like the key steps towards adding labels. We have an expert trajectory given, which is these. In this illustration, is these white circles, and we have an offline trajectory. So in this large data set, which is this blue trajectory here. What's happening is we compute a cost matrix. So in an optimal transport setting, we compute a pairwise cost matrix of like how far is this data point here from all the other data points in the expert trajectory. So we build this kind of cost matrix here. We call an optimal transport solver and determine an optimal coupling. So in this particular case, the optimal coupling would be kind of like this point would be associated mostly with this point here and a little bit with these points here. That's also plausible. And then the last step is we compute imitation rewards for each step. And that allows us to label offline trajectories with rewards. So effectively, what we do is, so once you have the cost matrix and this optimal coupling, you can multiply these two together to get some form of reward. In practice, we map this to an exponential and put a minus in front of it. So here's how this entire thing fits. So we have the expert demonstration. We have this kind of like box that assigns labels. And then we can use any offline RL algorithm to basically put everything together into an offline imitation learning setting. Now, question is, does this kind of idea work? So we looked at a bunch of test benchmarks in the D4RL suite. We matched the performance of offline RL algorithms where they have oracle rewards, so ground truth rewards given. That means the labels that we automatically assign to an unlabeled data set are sufficiently good to match the performance of reinforcement learning offline RL algorithms that work with ground truth rewards. So we don't see any significant difference here. The labeling is also fast. So we can label 1 million steps in 2 minutes on a GPU. So now in comparison with other labeling algorithms, so this is the method we propose. We have environmental return, so ground truth labels on the horizontal axis, labeled reward on the vertical axis. Ideally, you have something that looks like a straight line. Other methods kind of like have either more noise or more variance in their labeling, or they can't really distinguish between non-expert trajectories because they all get assigned the same kind of like reward, which is in this case 0. So that's also very encouraging. That kind of is an indicator why the automatic labeling actually works well, that it matches the performance of other offline or offline RL algorithms with ground truth rewards, because it's more or less it's very close to the ground truth. So to summarize just this last part, we talked about optimal transport-based labeling of unlabeled offline reinforcement learning data given expert demonstration, so at least one. The labels can be used by any offline RL algorithm, and we leverage large offline RL data sets to learn good policy within then an offline imitation learning setting.
Yeah. Could you extend these ideas to the conversational setting? Or how much is it reliable geometry?
Oh, that's a good question. I haven't thought about this yet. So questions about whether we can use the same kind of idea to I guess in a natural language context. I don't know. We haven't built in anything specific about the geometry here. Yeah, maybe worthwhile trying out. Okay, let me just briefly wrap up. Overall, I wanted to make a point about data efficiency in reinforcement, in robotics and in reinforcement learning, why this is a challenge. We talked about 3 pillars of approaches for data efficient learning in robotics and reinforcement learning. So one, in the beginning, we talked about model-based RL, where we had a learned probabilistic model for fast learning from scratch. Then we talked about meta-learning using latent variables that allow us to generalize knowledge from tasks that we have seen before to tasks that are new but somewhat related. And in the third part, we talked about an approach for automatic labeling of large data sets for offline imitation learning. In that sense, yeah, thank you so much for your attention. And if you have more questions, please do.
Questions from the audience?
So for the latent variables for meta learning, are you simply telling the model sort of what the dimensionality of the changing variable spaces, and it's figuring out what variables to learn there?
Yes. So what we have to fix, or we fix the dimensionality of the latent space, and then it infers kind of like the geometry of that latent space from the data. We haven't done any kind of like extensive experiments of like figuring out what the right dimensionality is. In the setting that I mentioned earlier, it was kind of like clear because we changed 2 parameters in the setting, like the mass and the length of the pendulum. So a 2D embedding space is probably fine. But we didn't really try out many or much more complicated settings where it's unclear what the latent space should look like, how or what a good way of like finding a good or appropriate dimension is.
Oh, wait, say if you know the mass and length of a chain, you just plug that in, would it get the right answer automatically, or is there still some fine-tuning to be done after that point?
If you know what the mass is, so that, yes, so we have an extension of this where you can add additional knowledge, and you also can have like more general task descriptors like vision inputs and something like this. But so then I would go to this particular framework because that's a better way of incorporate specific knowledge as like fixed parameters. But there is a way of doing this, yes.
And it's like in the first part of the model, you say you learned one model, and in the next 2 parts, the meta learning and offline, I'll actually learn only to learn the model, and offline I will actually learn some policy. How do you see? How do you build? If you want to use offline data to train a better world model so that you can interact with it and improve your policy, or directly learn the policy from this data?
Okay. So the third, so you're correct. So the first 2 parts, we did learn a model of the environment. In the last part, I didn't say anything about models or non-models because the last part was just about adding labels. So if you want to use a model-based RL algorithm, then you can do this in the last part as well, or you can use a model-free algorithm. I'm sure I avoided the question that you actually wanted to ask, or
policy from the offline data. Yeah. Another question that I'm curious about is the second part. And I'm wondering how you discern the part related to the task and the part which related to the general model. So
Sorry, can you repeat?
for instance, how do you know which part is related to the parameter you feed into the model such that it's related to the embedding, and which part you should learn generally?
Okay. Yeah. So you have your, I'd say you have your, say you have some form of like a regression model, and you just use all of those parameters of the regression model. It doesn't really matter whether it's a neural network, Gaussian process, whatever. That's your global parameters. You augment your parameter set with this H variable. You just take a classical, all the model parameters you have, they are global parameters, and you add more parameters. And these are the task-specific parameters.
You learn that parameter or you
H,
give it?
H is learned.
It's not like
No,
totally something.
no. So we put a prior distribution on H and then compute an approximate variational posterior distribution on those latent variable. And if you make predictions, you integrate them out. So I didn't specify that here because that would go maybe a little bit too far. But it's a fully Bayesian setting or approximate Bayesian setting where you find a posterior distribution on the latent variable, and when you make predictions, you integrate it out. So, one last question?
Thanks for the great talk about marketing environments. So I'm wondering, when computing the optimal cost and optimal transport plan, what distance metric we're using? Are you using something like cosine similarity between like the states?
Yeah, so we used Wasserstein distance and the cosine similarity.
Do you think this can scale up to like high-dimensional observation spaces like images?
Possibly. Yep. But yeah, I'm happy. But yeah, we haven't tried this out yet. So it's yep, happy to think about it more or chat about this.
All right, so we are at time. So let's thank Marc again.
Thank you.